Hello everybody, welcome to another drive-by code session. So my friend WaiKit and I, we have been talking and we decided that we're going to start a new series on how to create programming languages. This is, I think, going to be quite a lengthy series, and I hope that you come along for the ride. As usual, WaiKit is going to come out with all of the code examples, and I am going to replay his code sessions and then explain what he did. For the first episode in this series, I thought that I would give an overview of what it's like or what it really means to be creating a programming language. So when you're programming when you're creating a programming language, what you need to do is write a program, which is no different from what you're normally doing at the job as a programmer. Now this program is going to take in as input the code that is written in your programming language. This might be a programming language that you are inventing, but it could also be a pre-existing language if you decided that you want perhaps to make improvements to this language, or you're going to come up with a better version of this programming language. Now your program is going to take this code as its input, and as its output is going to produce what? It's going to produce machine code. It's going to produce machine code, which is a set of instructions to be carried out by your CPU, your central processing unit. This is a unit in your computer. Let me see. There it is. So this is what a CPU looks like. And you're producing machine code, which is code that this CPU, this chip in your computer, will carry out. So a CPU is responsible for all of the smarts in your computer. So pretty much anything that you can think of that a computer can do, at some point in time, it's going through this chip to do it. So the CPU is the workhorse of your computer, and then you're going to give it a program in the language that it understands. So, and I'll show you in just a bit what that machine code looks like. And this architecture is what a lot of programming languages use. And if you follow this architecture, then the program that you're writing here is called a compiler. And programming languages that use this architecture, they are called compiled languages, compiled programming languages. And some examples of these are C, C++, newer languages that are this way are Go, Rust, and Haskell. Now this is not the only kind of architecture that programming languages can have. But before I go on to the other ones, I want to give you an example of what this machine code here, what that looks like. We're going to use a C program because, as I just mentioned, C is one of those languages in this family of compiled languages. So this is a C program, and WaiKit chose the Fibonacci series, one of the most cliched examples in programming. So this is the input to the compiler program, right? This is a fib.c. It's a program written in the C programming language. And the compiler program that is going to take this code and translate it into machine code is called GCC. And it's available on most Unix or Unix-like systems. So if you want to compile this program into machine code, you say GCC, the name of this program, and then you tell it what is the output file, the name of the output file you want it to be. I'll call that fib. And then it creates this fib file, which is a binary file. So my editor doesn't support binary files, but I'm going to use one that can. It's called hexfind. So if I use hexfind to look at the contents of this binary file, then I see this. All of these are a series of binary numbers, and this is the textual representation of the data. Some of it is readable and some of it isn't. This is the initialization section of the program, which has some strings in it, so you can actually make out some of it. A lot of zeros will follow, and then somewhere down in the middle of this file, there's some interesting code here. Now, unless you are an expert in machine code for the particular processor that these instructions are for, you won't be able to really understand what's going on here. However, you can tell GCC to output a slightly more human readable format that will give you an idea of what's going on with the -s option here. So I'm gonna ask GCC to compile it, but this time output also a .s file. And the .s file is what is called assembly language, which is a low-level programming language for the purpose of basically writing the machine code instructions directly to a particular brand of CPU or a particular class of CPU in a slightly more human readable way. So I'll show you some of these. So for example, this move L instruction is saying, can you move the value 0 to this address location in the memory? And we have a few of this: move the 0 to this address, move the 0 to this address. And this, what this address is that RBP is a register that has a number that represents some memory location. This -A is an offset from that location to move it, to give you a particular slot. So this offset 8 is one memory space, offset 12 is another memory space, and offset 16 is yet another one. So these three lines actually correspond to these three lines in the C code, which are making variables. And then here, I'll show you just a couple more instructions. This is compare and jump if greater than. These two lines are there to make the while loop work. So this is basically saying compare the number in this address location and compare it to the value in this register, which one of them is one of them is the other. And then the next line is saying if one is greater than the other, we're gonna jump from here to here, but otherwise we'll move on to the next instruction. So you can see that there is a programming language that your CPU understands, and it's very low level and it's harder to follow than normal programming languages, but it is there and it works. It actually works really well. So if you can manage to generate these sequences of instructions in this format for your CPU, then from sort of a programming language that you designed and invented, then you can have a working programming language. Okay, now what's another type of programming language? Okay, so another programming language architecture looks like this. So you're still making a program, but this time the program you're making, and the program, this one, you're still making a program, and your program still is going to take some code as its input. But this time, your program is going to execute and directly return the results of executing the program. So this program is actually executing the program and not just producing machine code to be run in the CPU. If you adopt this architecture, then the program you're writing is called the interpreter. And programming languages using this architecture, they're called interpreted languages. Some examples of those are Python, Ruby, and JavaScript. One advantage of this architecture is that you don't need a compilation step, which means it can start up faster, because sometimes the compilation step can take a while to finish. But the disadvantage is that the running time of the program is not quite as speedy as compiled languages, because machine code ran directly on a CPU is really fast. So to give you an example of that, WaiKit also wrote this Fibonacci program in JavaScript, and we can execute this using Node.js. And there it is. It ran the program, and it produced the output directly without going through an extra compilation step. Another type of programming language is called transpiled languages. That looks like this. These are called transpiled programming languages, and examples of them are TypeScript, Elm, and CoffeeScript. I'm gonna credit CoffeeScript with popularizing the notion of transpiling languages to JavaScript. But let me talk about what that means to be a transpiled compiler language. When you're using this architecture, the program you're writing is called a transpiler, and it's gonna take in the code in the source language and generate code in the target language. But this code is still code, it's not direct machine code. So this code might be JavaScript is one popular target programming language. C is another popular one because there's a lot of existing infrastructure for compiling C. Once you have code in this intermediate programming language, which again is still not machine code, then you use another program to either convert this code into machine code, or the other program could be an interpreter, which in the case of JavaScript, that's the case, that will execute that program directly. And the nice thing about this that makes this easier to do than perhaps the other architectures is that this other program, you don't have to write it because you're relying on existing infrastructure to do the next step. So you don't have to worry about, like with JavaScript is a browser will execute JavaScript directly, and with C is there's already well-established tool chains to compile C to machine code, so you don't have to do that step. All you have to do is translate the code in your programming language of choice and convert it to this second programming language. And as I said, an example of that is TypeScript, so I'll show you TypeScript doing that. So this is the same program written in TypeScript. It looks mostly like JavaScript because it's meant to do that. And if you go to the TypeScript playground, you can put in JavaScript code, and then it'll immediately produce the equivalent JavaScript code, which still looks mostly the same as the left-hand side here. And then this JavaScript code will simply get executed in the web browser, which is what makes everything work. And you didn't have to implement the web browser yourself because there are perfectly good web browsers out there available for free. There's one more architecture which I want to cover, which is slightly more complicated. That looks like this, and this is called a bytecode interpreted programming language, and examples of these are Java, C#, and in fact JavaScript. And only over the past 10 years or so has JavaScript moved over to this family of languages. Before that, it was simply interpreted. So how bytecode interpreted programming languages work is we've introduced this notion of a VM bytecode. And this bytecode is something that was newly invented, and it's sort of like machine code, but not exactly. So this is like machine code, but it's not platform specific. It's still very low level. but it's not quite to the low level of a real machine code. So your program, your compiler is going to take your code and generate VM bytecode instead of actual machine code. And then this VM bytecode cannot be executed directly by your CPU. It needs a bytecode interpreter in order to execute it. So, and this bytecode interpreter, as the name suggests, is an interpreter, and you still have to write this guy yourself. And because it's an interpreter, its job is to output the results of the program. So in order to run the actual program, you first have to compile it into bytecode and then run a bytecode interpreter which will execute the code and yields the results. Now, the internals about how the bytecode interpreter works is as follows. The bytecode interpreter actually has to bridge the gap between what the bytecode looks like and what the machine code looks like. So inside of the bytecode interpreter, and this is where the term JIT, which stands for just-in-time compilation, it will actually, let me use a different color here. It will actually compile this machine code. It will actually compile this bytecode here into machine code, and this guy is called the JIT compiler. It'll do this on the fly. So it takes the bytecode, let me color this in. It takes the bytecode, translates it into this machine code, and sends it to the CPU on the fly on a function by function basis. It doesn't do the entire thing. It does each function as the function is needed. And this is an approach that is more complicated. It's basically a hybrid. It's an attempt to have the best of both worlds of the compiler architecture versus the interpreter architecture. So this last kind of architecture, I'm gonna defer that perhaps until the later parts of the series because it's by far the most complicated. Starting the next episode, I'm actually going to drill more into the contents of this box, which is the program. And so the program, whether it is a compiler or an interpreter, in either case, the program is going to need something that can take the code and make sense of it. And that thing is called the parser. And the parser is going to produce something. What? Well, that's what you're going to find out in the next episode. So if you want to come along for the ride, stay tuned. I hope you enjoyed this episode, and WaiKit and I will see you next time.